Today we consider another method of linear classification alternative to logistic regression. This method is called linear discriminant analysis. Why do we need another method when we have logistic regression? There are several reasons. Firstly, when the classes are well separated, the parameter estimates for the logistic regression model are surprisingly unstable. Linear discriminant analysis does not suffer from this problem. Secondly, if the number of predictors is small and the distribution of the predictors' axis is approximately normal in each of the classes, the linear discriminant model is again more stable. And thirdly, although logistic regression works with more than two classes, it is more usable for two classes. That is why linear discriminant analysis is more popular when we have more than two response classes. In logistic regression model, we use sigma function to model the probability of belonging to the kth class. Another approach of estimating the probabilities of belonging to the kth class is to model the distribution of the predictors separately for each class K, and then to use Bayes' theorem to obtain estimates of belonging to class K given the value of predictor equal to x small. Let's consider this formula. Here, in the numerator, we have different types of probabilities. P of y be equal to k is a prior probability that a randomly chosen observation comes from the kth class. This probability is a prior probability that x large is equal to x small if it lies in the kth class. In other words, this is a density function for x in the kth class for a discrete random variable. But if x is continuous, it would correspond to the probability of x falling in a small region around k, around x. The following types of the probabilities we can also find in the denominator, and in the left side of our formula we see a posterior probability that the observation belongs to the kth class, given the predictor value for that observation. Now we will use such a variable notation to rewrite our formula. By the Greek letter P with the index k, we will denote the prior probability of the kth class. By fk of x, we denote a prior density function of x. And by pk of x, we denote a posterior probability that the concrete observation belongs to the kth class. Now we can rewrite the Bayes formula in a more compact way. And we classify x as class K if the probability of belonging to the kth class is maximal among all the posterior probability of belonging to the class I. For now, assume we have only one predictor. We would like to obtain an estimate for the density for kth class that we can plug into the resulting formula from the previous slide in order to estimate the probability of belonging to the kth class. To estimate density functions, we will first make some assumptions about distributions in the kth classes. We assume that all the distributions are normal. In the one-dimensional setting, the normal density takes this form. Here, mu k and sigma squared k are the mean and the variance parameters for the kth class. For now, we also assume that all the variances are equal, and we denote by sigma squared a shared variance for all the classes. The resulting formula from the previous slide will take this form. Thus, to solve the classification problem, we should solve the maximization problem for the formula 2. We need to maximize the posterior probability of belonging to the kth class. To simplify the solution of the maximization problem, let us logarithm this formula. Now we deal with this formula. First of all, we can reduce this fraction, removing the duplicative expressions for numerator and denominator. Now we will remember some important properties of logarithms which will help us to work with this formula. First of all, the logarithm of a fraction is a difference between two logarithms. A logarithm of a product is a sum of logarithms. When we log the exponent, we get the power of the exponent. Logarithm of 1 is 0. Now we use these properties and rewrite our formula. First of all, we work with the numerator. Here we have a product of two expressions. We can rewrite it as logarithm of pk. Then we can change this product into sum of two logarithms. And using the rule that the logarithm of exponent is the power of exponent, here we get minus the fraction which was in the power of the exponent. This was our numerator, and minus logarithm of the denominator. To write in short, we will use these dots for the denominator. Now we need to open these brackets, and we will get logarithm of pk minus x squared 2 sigma squared plus x times mu k over 2 sigma squared and minus mu k squared over 2 sigma squared. And again, the last expression minus logarithm of the denominator. Now let us underline the expressions that depend on the k class, which will be different for different classes. This expression depends on k. This summand doesn't depend on k. This one depends on k. Again depends on k. And this logarithm doesn't depend on k because the denominator is the same for all the classes. After simplifying the formula 2, we've got an expression sigma k of x, which we need to maximize among all the classes to get the class with the largest probability. And this will be the solution of our classification problem. On the previous slide, we derived the decision rule for a Bayesian classifier. And now we look at the example how this decision rule works. Assume that the probabilities of belonging to the first and the second classes are equal. So the prior probability P1 is equal to the prior probability P2. Now we ask the question, when the Bayes classifier assigns an observation to class 1? According to the decision rule, when sigma 1 of x is larger than sigma 2 of x. This means that we should solve this inequation to get the decision rule for x. After some simplification, we get that x should be larger than the average value of the means for two classes. Let's look to this picture. Here we can see two classes, which are denoted by class y1 and y2. We suppose that the density for the first class is a normal density with a mean μ1 equal to 3 and some variance. The density function here is drawn in blue. The density function for the second class is drawn in red, and here the value of mean is equal to 0. Now we will find the decision boundary for this case. If we solve this inequation, we get that x equal to 1.5 will be the decision boundary. In the picture, it is represented by this vertical black line. We have derived a decision rule for a Bayesian classifier. First, we calculate such a function sigma k of x for each class, and then we assign x to the class with the maximum value of this function sigma k. But in practice, even we are quite certain in our assumption that x is drawn for a normal distribution within each class, we still don't know the parameters. And usually we even don't know the prior probability of belonging to k class. So all these variables are unknown, and we need to estimate them. And if we use the following estimates for the means, variance, and the prior probability pk, we get a new classifier, which is called linear discriminant analysis. So here we firstly calculate a discriminant function, and then we assign x to the class with the maximum value of this discriminant function. The word linear in the classifier's name stems from the fact that the discriminant function is linear function of x. Now we turn to the case when we have more than one predictor. Suppose that each object is described by n characteristics, the variables x1, xn. These are our n predictors. Also, we set an assumption that in each class, our variable x is distributed normally. It has a multivariate normal distribution with the parameters μk and s. Here, μk is a class-specific mean vector, and the covariance matrix S is common for all the classes. We get such a density function for the kth class. Now we plug this density function instead of fk and fi in the Bayes formula. And after performing a little bit of algebra, similarly for the previous case, we get a formula for a discriminant function for a multidimensional case. As we have discussed, linear discriminant analysis assumes that all the observations within each class are drawn from a multivariate Gaussian distribution with a class-specific mean and a covariance matrix which is common to all k classes. Now we set another assumption. We suppose that again all of the observations within one class are distributed normally, but not only mean is case-specific, but a covariance matrix is also specific for each class. Under this assumption, the Bayesian classifier assigns an observation x to the class for which this function sigma k of x is the largest. We can notice that this expression includes one summand where x is squared. That is why we can say that a discriminant function is quadratic. Now when we put the estimates for the means and for the covariance matrices, we will get a quadratic discriminant analysis instead of the Bayesian classifier. Now we turn to the comparison of two classifiers, LDA and QDA. While doing linear discriminant analysis, we deal with a covariance matrix which has m times m dimensions. So we need to estimate m times m plus 1 over 2 values of covariances. Whereas when we deal with QDA, we need to estimate k times more values of covariance. This means that QDA is more flexible and at the same time it has a higher variance. Therefore, if we have a large training sample, then a large variance will be not critical and quadratic discriminant analysis can show better results. If the training sample is small, and if the assumptions about the common S matrix can be true, then it's better to prefer linear discriminant analysis. And finally, if the covariance is clearly different, quadratic discriminant analysis should be preferred. Which of the studied classifiers is more preferable in practice problems? As we noticed before, if classes are well separated, then logistic regression sometimes behaves unstable. Its parameters often tend to infinity, unlike LDA parameters. Therefore, for better results, we should use linear discriminant analysis. Sometimes, oftenly in medicine and biology, we have bad separation of classes, and that is why we will prefer logistic regression. For the case of large sample size, when the distribution of each class tends to the normal, linear discriminant analysis is more preferable because it is more stable than logistic regression. Also, logistic regression is oftenly used in binary classification, whereas linear discriminant analysis is oftenly used for the number of classes more than 2. One of the advantages of logistic regression is that it allows to include squares of variables in the model. But if we want to include squares in linear discriminant analysis, it means we need to convert it into quadratic discriminant analysis.